can move slides back and forth, and we will be, okay. You should have gotten all the notification that it's going to start recording, because we're going to be going live in just a little bit.
I see. Okay, I'm going to sharing.
Yeah, just to check. Perfect.
Yeah. It works.
Perfect.
Right. All
yep,
right.
It
great.
works. Okay, and with that, we are still missing our first presenter, but we're going to go ahead and get started in the sake of time. So welcome, everybody. My name is Grace Lewis. I work at the Carnegie Mellon Software Engineering Institute. And today I'm going to be chairing this session on Software Architecture and Design 3. We have 6 presentations in this session, so this is one of the bigger sessions. We will follow the format that has been used in previous sessions that you have attended, which is that all presenters will present back-to-back first. Each presenter has 5 minutes. Please try to stay within your 5 minutes, because the idea is to have a lot of discussion at the end. What we're going to do is the following: as the attendees and also the co-presenters have questions, if you would like me to ask the question, please write the actual question down in the chat, and please let me know who it is addressed to. If you would rather ask the question yourself, which obviously we're a small group, so I welcome that, simply say, I have a question for this particular person, and we will do that. So with that, because we seem to still be missing our first presenter, we're going to go to our second presentation. So Michael, we're going to start with you. So our first presentation in this session is Terminals All the Way Down by Michael McInnes from Carleton University in Canada. Go ahead, Michael.
Okay, everyone can hear me? Okay, just going to share those. Okay. So, hi everybody, my name is Michael McInnes. I'm a PhD student at Carleton University. My supervisors are Professor Olga Basel and Professor Michele Lanza. As we're limited to 5 minutes, this is really a speed run of what we cover in our paper, Terminals All the Way Down, and the companion video. So we invite you to take a look at those for more detail. This talk is about using interconnected Unix terminals as the foundation for a new type of distributed and language agnostic development environment. Just so we're all on the same page, let's start with what's a Unix terminal. The first Unix terminal was the teletype. Teletypes were replaced by video display terminals, and video display terminals were replaced by window terminal emulators. We claim, as others have pointed out, that window terminal emulators have been quietly evolving into a general support environment for text-based programs. In parallel with this evolution, numerous integrated development environments, or IDEs, have been created. And IDEs have converged on what some call a bento box model, where the screen is partitioned into rectangular areas. This layout is remarkably consistent given the number of IDEs. This is even more surprising when we consider that popular IDEs share little, if any, code. Those code bases are also increasingly large and complicated. This makes life hard for tool builders who must target each specific IDE. I don't think VS Code, shown here, was the first to include a terminal, and it probably won't be the last. Our approach can be summed up as flipping that inside out. What if instead of embedding a terminal in an IDE, we could bring IDE-like features to the terminal? There are many people working on bringing IDE-like auto-completion to the terminal. In the video, we show BPython, and here we see Fig. Popular Unix shells like Bash and Zshell have been leading the charge here. And in addition, the language server protocol has really leveled the playing field. We, of course, want to leverage all of that, but it isn't our main focus. The real power of window terminal emulators comes from the ability to juxtapose them. We want to go further and connect them. We think many IDE features can be seen as the connection of juxtaposed textual windows. To name a few: being able to click on a file in a file tree or listing and open or jump to that file. Similarly, being able to click on compiler errors or linter output and jump to the corresponding spot in a file. Being notified while editing a file what other windows are saying about that file. And even things like side-by-side diffs or interactive debuggers seem to fit this model. Juxtaposing window terminal emulators is already possible. We're working on connecting them and have started on an architecture to allow that. This is covered in more detail in the video and in the paper. One of the key things we're doing is baking in the idea that terminals don't have to be interacting with the local machine. The terminal has always been a portal. It can interact with a local machine, a remote machine, or a container. Enabling all of this is the ability to pass messages. We are currently encoding messages as an escape sequence using an escape sequence known as a privacy message. Privacy messages are ignored by Xterm-like Windows terminal emulators, which is to say pretty much all Windows terminal emulators. With these messages, we can multiplex connections. This gives us the ability to create a component that is aware of what all the terminals are doing, as well as the ability to launch additional terminals as required, not only locally, but on remote machines and in containers. As we mentioned in the video, work on this has started. We can currently launch terminals locally, remotely, and in containers, all of these connected to local Windows terminal emulators. Our next step will be to recognize what some people call code addresses in output, and to see if there are existing terminal-based editors that we can easily extend as a proof of concept. We'd love for others to take a look. Let us know what you think. Thanks for listening.
Thank you very much. I really enjoyed the terminal-like slides. Very cool.
Thank you. Thank you.
Okay, so we still don't have our first speaker. I just sent them an email message. Hopefully they'll join soon. I know that there has been some confusion with the time zones. So we are going to go ahead to our second presentation by Carlos Gavidia Calderon from the Open University in the UK, titled, "What Do You Want From Me? Adapting Systems to the Uncertainty of Human Preferences."
Okay. Can you guys see my slides?
Yes.
Oh, brilliant. Oh, well, thank you guys for the presentation. I have to say, like, really impressive Spanish. Pronunciation was flawless. Well, I'm going to start. Well, I'm Carlos. I am a researcher at the Open University, and I'm presenting today my ICSI paper. Well, like, in some scenarios, autonomous systems need the cooperation of humans to be able to accomplish their goals. This is especially relevant in emergency situations where rescue robots are used extensively for search and rescue. What you're seeing on the slide is a rescue robot called Hector, developed by the Technical University of Darmstadt, and it has some autonomy capabilities. It can navigate these certain areas, it can detect survivors. However, Hector is a small robot. So like if Hector finds a survivor that's able to move, Hector can guide them to safety. But if the survivor is not able to move, a robot like Hector will need help to evacuate the victim. Now, an initial thought would be like, let's get help from professional trained first responders. However, in most emergencies, first responders are scarce, mostly busy, so they might not be available to help a robot with evacuation. But first responders are not the only one able to provide help. What you're seeing on the slide is a picture of the floodings that happened in Peru in 2017. And as you can see in the picture, people actually help each other during emergencies. And social psychology has an explanation for this phenomenon. They state that strangers or people with nothing in common, when they experience together tragedy, there's a shared identity that emerges. And people sharing an identity tend to show solidarity towards each other. So what we propose in our ICSI paper is an autonomous system that can capitalize in this emergent solidarity so it can accomplish the evacuation goals. Well, such robot, when it's deployed into an emergency, will sometimes face people that have developed this shared identity, so they are keen on helping other survivors, and some people that don't, that they didn't develop the shared identity, so they will prioritize their own safety. And to make things a bit more complicated, identifying or detecting a shared identity is hard for the robot and arguably hard for us humans. So a robot will need to adapt and make a decision with partial and incomplete information. And to be able to accomplish this, in our paper, we proposed using game theory. Within game theory, there's a modeling framework called Bayesian games that are used for modeling and decision-making under uncertainty. They are widely used in economic design for auction design, to name an example. What you're seeing in the slide is our proposed architecture for a robot that, when facing a human, It builds a game theoretic model of the interaction and uses the insight from this model to make a decision. Our architecture is inspired in the MAPE-K framework for autonomous systems. Now, we did a preliminary evaluation of our approach, and we developed like a simulation of a simplified search and rescue scenario, and we compare our identity-aware robot with two competitors. One competitor, we call it the pro-self-oriented robot that never asks for help from survivors. And the other competitor is the pro-social-oriented robot that always, every time, asks for help from other survivors in the area. We simulated 4 scenarios, and in all of the 4 scenarios, our identity-aware robot performed better regarding average expected number of evacuations. That's basically all I have to say today. To recap, for humans and systems to cooperate, we need systems that understand human preferences and adapt to them. This is especially relevant in emergencies where autonomous systems can actually profit from the cooperation among humans. And game theory and social psychology are tools that can help towards accomplishing this. Thank you very much for your time.
Thank you very much, Carlos. Very interesting. We are going to go to our next presenter, Sheng Li, from the University of Concepcion in Chile, correct?
Yes.
I'm also kind of cheating because I see the flag.
Okay,
And
yeah.
the title of his presentation is Just Enough, Just in Time, Just for Me, Fundamental Principles for Engineering IoT Native Software Systems.
Okay, so do you see my screen now? My slide?
Yes.
Yeah.
Yeah.
Because I don't see the, okay, thank you, Grace. Hola a todos, buenos días, buenas tardes y noches. My name is Sheng Li. I'm from the University of Concepcion in Chile. Today I'm going to talk about some fundamental principles for engineering IoT native software systems. Well, I have to skip the explanation about what Internet of Things is, but I believe all of us must have known about it. But I need to, let's at least clarify the concept that when we talk about IoT systems, we are talking about the software systems, all right, at least in the current context. Well, for the IoT native software systems, it's been widely recognized that we need not only new tools and technologies, but also new understandings of the systematic development process and tasks. Okay, that's why we have been suggested zooming out from the lower level technology view to the much higher level view of the whole system and its engineering. All right. So in terms of the higher level view, we emphasize the software engineering principles. Okay, because they are abstractions of the best practices. So we believe that there should be also principles, software engineering principles, for the IoT software systems. All right. So the question is, how do we abstract or extract those best practices? Well, firstly, we observe. The first principle, just enough, is mainly based on our observations. Actually, we believe these are already kind of common sense now. For example, we all know that we should avoid over collection, over processing, or over storing the data. All right. It's not only for the not only about the performance or resource concerns, but also about the privacy concerns. Actually, if you attended the previous keynote speech, our Wednesday keynote speech just mentioned how important the privacy preservation for and in software engineering, right? Although there can be some trade-offs. For example, we can intentionally store some intermediate results to reduce some intermediate data processing workloads, all right? And the second approach to extract best practices is to practice itself, okay? The second principle, just in time, is mainly based on our current practice, although there can also be some trade-off between the first two principles. And our current practice is to improve the communication efficiency in the IoT environments. It's impossible to explain those techniques, but we can imagine that there are quite a few different techniques to improve the communication efficiency in the IoT environment. But the problem is, all the techniques will cause extra data processing workloads. It's unavoidable. There's no free lunch, right? So there's a very frequent question is it really worth it, especially for those complicated techniques? Well, we have been using our second principle to answer this question and also to guide our research. All right. We argue that as long as we guarantee the key data to arrive at least in time, or the key tasks to finish at least in time, it'll be worth it. So this is the second principle just in time. And the third one is, at this current stage, is mostly a proposal, but it's also based on our experience and our observations. Just for me, we argue to make those functional units smart, just like those smart individual devices in the IoT environments and in the smart environments, smart office, smart home, and smart everything. All right. But we argue to make them the functional units smart in a very selfish way. This principle is to address the kind of the problem, in our opinion, the problem of overusing the orchestration mechanisms. Actually, we already prepared something to argue with the authors of the first paper. Unfortunately, they are not here. But we very interestingly, we have different opinions in this case. We believe that our observation is that most of the current IoT solutions are largely rely on the orchestration mechanism, and there are many disadvantages of that. So we advocate that we can follow this just for me principle to at least reduce the usage of the orchestration mechanism, to reduce the usage of controllers everywhere in the previous scenarios. For example, in this, take this illumination scenario as an example. Imagine I am the ceiling light. Okay, so what I need is just a semantic notification, and I will make smart decisions by myself to turn on or off. You don't have to instruct me how to do it, and I don't care about who sent me this notification, no matter it's a door, a movement, or projector, because that's not my business. Okay, so I don't have to worry about those door opening or project on events then. In contrast, I need to be aware of those brightness sensors because they will be offer useful information for me to make those smart decisions. All right, so this is just for me. I mind my own business. To conclude, well, actually this work confirms the other researchers' conclusions. All right, we believe that we need dedicated efforts, techniques, and theories for engineering IoT native software systems. And we believe that we need more principles, software engineering principles, because some principles might be more fundamental and some others might be still more technical. Okay. Muchas gracias. That's all for me.
Very interesting and a little controversial. I like that. So our next presenter is Anas Nadim. Thank you for joining us. I know that there have been some problems with the time zones and that, but we're glad that you're here. So our next speaker is Anas Nadim from North Dakota State University, and he will be presenting a case for microservices orchestration using Workflow Engine. So go ahead and share your slides, Anas.
Grace, thank you for the introductions, Grace. I hope everybody can hear me. I have shared my screen and I hope everybody can see that too.
We can see your screen, but it's not in but it's not in presentation mode.
Still not?
Yes, it's perfect. Thank you.
Okay, awesome. All right. So my name is Anas Nadim and I'm a graduate student at North Dakota State University, and I'll be presenting our book titled A Case for Microservice Orchestration Using Workflow Engines. Before we dive into the presentation, let's take a look about the need for microservices and why did we get there. In the past, or even currently, monolithic architectures are being used, which basically involves having everything in the same place. The communication between the components are local, and the pros of this is that faults are easy to debug using simple logs and breakpoints. However, the components become really tightly coupled and heavyweight and difficult to maintain. On the other hand, microservices allows breaking the bigger application into smaller applications that run in independent processes. In turn, the application is loosely coupled, scalable, and distributed in nature, which means in case a microservice fails, we can have multiple copies of that same microservice and forward our traffic to that copy of the microservice, and the system can continue executing even if in case of failure. So the deployment of such microservices is actually spanned on multiple machines, which may be in different regions, and a single process between these microservices can, a single business process can span across multiple microservices. So considering this nature, that communication between multiple microservices is done through mediums such as network. In front of you, you see an example of 3 microservices communicating over the network to cancel a ticket in a benchmark system, the details of which will be further in the presentation. So the motivation behind our work is simple. Microservices are complex due to their dynamism, and understanding the interactions is troublesome. So basically, our work intends to explore ways to make this interaction simpler and ways to make debugging easier and efficient. So basically, there are 2 main modes of microservice interaction. The first one on the left is orchestration, where you have a central coordinator that directs the communication between the services. And on the second, on the right, you have choreography, in which the services themselves direct their communication through events or directly calling the service. So choreography has been more prevalently used because the implementation in choreography-based approach is easier. And as my fellow mentioned, we will be talking about his question as well. But what happens is, as soon as the number of microservices in this case increase, we also believe that there is no such thing as free lunch, and the technical depth is embedded inside business process. So for longer, for systems that have large number of microservices, the process is actually rooted between the business processes themselves. So the result is very complex debugging in case of large-scale systems. So we make the following contributions. We port the largest benchmark to the best of our knowledge to orchestration, which was implemented priorly in choreography-based technique and observed its benefits. We highlight the practices for debugging of 22 injected bugs that were available in the benchmark system. And we compare our results with the original results of the benchmark and see what improvements we have been able to make. For this task, we use workflow engines, which are basically low-level distributed programming frameworks that allow the developers to focus on business logic. Examples of such are Netflix Conductor, Apache Airflow, Uber Cadence, and Temporal. So the reasons we chose Temporal for this study was that first, it offers a very programming language-based API, which makes the implementation easier, and then it has an extensive framework support for debugging. The benchmark that we considered contains 30 microservices that replicate fault from 22 fault cases. We map all these fault cases into code recognizable by the temporal orchestrator and then systematically debug them. This is how an interaction in the original system looks as a workflow. The details of how this mapping is performed is discussed in detail in the paper. So the user in our case study has 2 years of experience. They had no prior knowledge of the faults, and they went through elementary training of the debugging support available on Temporal. The main steps that were involved in the debugging process was first problem space construction, in which Scalax trace and visual trace were collected from the logs or Temporal Web UI, which is an internal part of the Temporal. The second was identification of the fault symptoms, in which we also had a minimalist environment setup, including only the microservices involved in the faulty process. And then we compared our results with the original. Third was fault diagnosis, in which we used the trace and the stack trace to again hypothesize the location of the fault. And finally, we used the solution generation and verification to resolve the issue, and then verified using test cases. So this chart shows our results as compared to the original debugging time from the benchmark study. In gray, you can see the time taken by users in the original benchmark study to debug the faults, whereas in the orchestrated approach, the blue bars highlight the time taken by the user in our study, which clearly highlights that the time taken by a user in an orchestrated approach was lesser than the time taken in a choreographed approach. So in conclusion, In conclusion, what we did here was we ported a benchmark system, train ticket, to a fault-oblivious stateful workflow model. We replicated faults to assess time to debug in orchestration mode, and our study provokes that orchestration is advantageous over cryptography as it makes debugging easier and faster. For future work, we plan to complete the study with more participants, port more benchmark to Temporal, and study performance on availability issues, and study other workflow engines to see if they have similar impacts. Thank you for listening to our presentation. That would be all by my side.
Thank you very much, Ennis, for the presentation. Next presentation, this would be the fifth, is by Philipp Heindl from the Software Competence Center in Hagenberg in Germany. And he's going to present towards a reference software architecture for human AI teaming in smart manufacturing.
Thank you. Actually, Software Competence Center Hagenberg is in Austria. This is the only thing. Yes, as you said, my name is Philipp Heindl. I'm from no matter, the countries are quite similar. From the Software Competence Center in Hagenberg, and my talk is about the software reference architecture for human AI teaming in smart manufacturing. So basically, the project that I'm talking about is an EU-funded project in frame of the Horizon 2020 project, and tackles, as the name suggests, how to improve the collaboration between humans and AI systems in smart manufacturing. And from a high perspective, we have here four main challenges that are addressed by this reference architecture. The first is the scalability of industrial IoT data processing. And to tackle that challenge, we decided to apply a Lambda architecture that will be later on described in more detail how that can be applied to the architecture. The second key challenge pertains to the validation of ethical policies, particularly in an AI context in manufacturing. And in this regard, we differentiate between two aspects. We differentiate between introspection and policy evaluation. The first, the introspection, being the autonomous runtime verification of the AI system. So this is triggered by the AI system itself upon detection of suspicious patterns. And the second part of the validation relates to the policy evaluation. And in this regard, it is about the checking the compliance with context-specific ethical policies. For instance, there's also been elaborated on by works from Google. The third main challenge relates to the relational machine learning and knowledge graphs. And in this regard, it is, so to say, the main focus is on the performance of graph embeddings. Graph embeddings is a technique to convert a graph representation as, of course, which is typically in a knowledge graph and RDF representations, for instance, to a vector representation. And this typically is associated with high performance and resource costs. So this is the challenge here. In combination, we have another challenge here, and this pertains to the orchestration of complex machine learning tasks across different frameworks. So of course, we have a bunch of different machine learning frameworks out there, but the question is how can we generically integrate in such a reference software architecture? And the fourth and last challenge pertains to the experimentation of data and algorithms. So there we have the vision to somehow end up in having a kind of DSL, so to say, that allows also non-experts to explicate in an operational manner how experiments can be optimized and conducted by a software system based on this reference architecture, and also how qualitative expert feedback from human in the loop, for instance, can automatically integrate in such an evaluation. This shall give you just a very rough overview about the rough software architecture. Of course, I do not have the time now to dig into each detail now, but it gives you an impression of how this Lambda architecture here reflects. So we have three different colors for the different components or layers, so to say, of the Lambda architecture. The first is the batch layer, so this is not that critical. And this typically involves components in this reference software architecture that allow to import models. So this is a batch import and authoring tools that, as the name suggests, allow you to edit the models. The second layer of this architecture is the speed layer. So this is where we have very strict and high latency requirements. So this is on the one hand components that are directly associated with production line systems. So this means IoT sensors, manufacturing systems, and also of course the HMI between a human operator and a machine there. On the other hand, we have components such as the knowledge graph, where also, as the name suggests, where we also have different charts for reading and writing to also optimize in that regard. We have components for graph-based machine learning, where, as I already said, we have the challenge of calculating the graph embeddings and the relation machine learning. And at the center of this architecture, at the bottom, we have the teaming engine, where this is the central coordinator, the orchestration engine across all the different components of the architecture. And the third layer pertains to the serving of the data and the results of it. And this covers on the one hand the operation support. So this is also kind of direct interaction with the human operator, where we give him the recommendations for the smart manufacturing context on the one hand, and the other components are the machine learning experimentation and the introspection policy monitoring. So this is about how to validate whether the whole system in operation also applies to the FDD policies. So what are the next steps? What we're currently working on? Currently, we're working on a reference implementation of that architecture to not only have it on diagrams, but also on code. And for that purpose, we're currently working with Flask and Spring Boot microservices. We're using, because we're working with only microservices, Spring Boot for service discovery. So this is a very operational part on the one hand. The second part is we're developing a quality model for human factors in smart manufacturing. So this is less a computer science, but more psychological topic. But we're working on an operationalization of this quality model based on the Convoco model. And currently we're working on identifying the quality factors and metrics for them. The other parts we're working on are the policy model and the DSL for explicating the experimentation for the machine learning components and the quality evaluation. Yeah, if you have a lot of questions, which I hope, then I'm happy to answer them after the last talk then.
Yep. Thank you very much. And so last but not least, our presenter, our final presenter is Simon Biswas from the Iowa State University. And the title of the presentation is The Art and Practice of Data Science Pipelines, a comprehensive study of data science pipelines in theory, in the small and in the large. Go ahead. We can see your slides.
Great, thank you. So hello everyone. This is the presentation on the art and practice of data science pipelines. I'm Suman Biswas, and this work is in collaboration with Mohammad Wardat and my PhD advisor, Professor Ridesh Rajan. So today we have availability to numerous data in different forms, and we are also experiencing a lot of new ML and AI technologies, which leads to development of new data science software and their uses in the practice. So in this paper, we wanted to study the design and architecture of this data science software. So here are two different examples of data science software. Here in the left, you can see a data science notebook taken from Keras repository. Here in different cells, different tasks have been performed, like pre-processing, modeling. On right, you can see a data science project where face classification. The software architecture looks like modularizing task and having the software structure into similar stages like training or serving models. So we have also seen a lot of examples of data science pipelines architecture presented in different papers for different purposes, like introducing new methods or proposing new techniques. So in this paper, we have studied the data science pipeline. The the canonical definition is basically the collection of data science stages from acquisition to cleaning or curation to modeling and so on are referred to as data science pipelines, as you can see an example here. And today we don't know what are the typical stages of data science pipelines and how are they connected, and do the pipelines actually differ in their theoretical representation and that in the practice. So in this paper, we contributed these things. So first, we have actually presented 3 different representative views of data science pipelines and their semantics and vocabulary. And second, we have actually shown analysis framework for analyzing data science pipelines from practice, like how we can analyze the architecture. And third, to draw inspiration from the existing pipelines, we have presented the state-of-the-art pipelines from theory and practice. And fourth, we have actually performed some comparative analysis to show what are the different types of pipelines and what are the existing issues in this kind of architecture. So we divided our study in these 3 different parts, in theory, in the small, and in the large. And first, we actually studied literature, and by using an open coding scheme, we standardized the representative views. And second, we have actually parsed notebooks collected from Kaggle, and then looked at the low-level pipelines in the small. And third, we also looked at large projects from GitHub and leverages some automated analysis and also some manual analysis to understand a pipeline in the large. So, for example, in theory, you can see a representative view of pipelines. We have seen 3 different layers, and under each layer, you can see different stages. We have found 11 stages and many subtasks, but most of the pipelines today are designed in an ad hoc manner, and there is no common terminology or representation that can facilitate like reuse or interoperability. And also, we have seen that many pipelines do not actually modularize the task into stages. These are 3 different kinds of pipelines that exist today in pipelines in theory. The first is the machine learning process, which basically builds predictive models using new supervised or unsupervised ML techniques. And second is the data engineering pipelines, which mainly focus on managing and analyzing large amount of data. And third, the team process pipelines, which actually are not software architecture, but the workflow of human activities and like how teams distribute their work. In the small, we have actually performed a API-based analysis. We looked at the documentation of data science APIs, like from scikit-learn or Keras, and also we parsed the AST from the DS notebooks, and then we used the API dictionary to create pipelines automatically. Here you can see many different stages from theory do not exist in the small, and we have found different anti-patterns, like all programs fail to maintain a good separation of concerns, especially data pre-processing is tangled very much with other stages, but some resolution attempts have been taken for readability, usability, debugging, or maintenance. And finally, in the large, we have analyzed large projects. Basically, we looked at high-level pipeline, which is the modular structure, entry points, and different manual analysis, and also the low-level pipeline, we looked at the source code. And it led to another representation in that we found that there are 2 different phases in pipelines in the large. First, the development phase, where the main goal is to develop the model artifact and not the prediction, but in the post-development phase, it's basically retrained or new predictions are made on new data set. So in this paper, we have actually made several instructions for researcher, engineers, or data scientists. And to summarize, we have presented the state-of-the-art pipeline analysis techniques and different anti-patterns. Let me know if you have any questions. Thank you very much for listening.
Thank you very much. Very good 6 presentations. So
Thanks.
we do have questions in the chat, which is great. So first question, Carlos, you have a question for Michael. Can you please go ahead and start with that one?
Yeah, sure. Hello, Michael. Great presentation. So I noted that in your presentation, you focus on Unix and Unix-like systems. I was wondering, like, maybe in the future you want to support Windows environments. I have read recently that PowerShell is getting some traction, and even some people in the Linux community are like going to PowerShell. I want to hear your thoughts about like how to implement your approach in Windows environments.
So I was encouraged when I saw what happened with Docker, where you had something that was so popular that systems that weren't Unix kind of bent over backwards to support it. And that kind of led me to believe that you increasingly don't need to target other platforms, that you can target Unix and the other platforms will follow. So so this is, and the other thing is that we're really trying to focus on developers who tend to use the terminal and other people who use the terminal, and those tend to be people who are using Unix and Unix-like systems. So that's probably the place to start.
Great, thanks.
Thank you very much. I know you have another one, but I'm going to switch over and then come back to you. Shengli, I'm assuming that if you typed your question, you want me to ask it. I'm happy to do that. Question for Anas. Choreography is generally considered more complicated, sophisticated than orchestration, according to the literature at least. So why do you think it is easier to implement?
Thank you for the question, Jenny. That's a really good question. So we do believe that either if it's orchestration or if it's choreography, there's complexity involved in actually laying out the framework or the framework for communication in both of those. But when we say that it's easier to implement, we actually mean that it's easier to implement it's easier to implement a microservice for the developer because they can actually have it listen to that queue or whatever even base that we're using, and we can just plug and play it. So it basically involves like you can just parallelly listen to that queue instead of like having to go and change some code. So that part of what we mean is like that is how what we mean by it's easier to implement, because it's easier to implement in the context of just plugging and playing microservices.
Yeah, I agree. It's debatable. Actually, this is just a side product question. I have two real questions to challenge you because I took a job from our track chair. So I may save some time later on for the others. Maybe the others can ask questions first, and then I will challenge you. Don't blame me,
awesome.
all right? This is a job from the
Awesome.
It's all my fault. It's all my fault.
No.
It's all my fault. It's okay. Perfect. So, Simon, you have a question for Philip.
Yeah, hi Philip. Great presentation. So I had a question about about the ethical aspects you talked about. So I was looking at also your paper. Like you have said that there could be verification and formal guarantees of ethical aspects. So what could be some examples? Can you share what guarantees do you think from the ethical perspective you can give to the AI models or the pipelines? Yeah.
I'm not quite sure if I understood you correctly. The question is about what kind of ethical guarantees and policies that we are talking about.
Yeah, and what kind of verification?
Yeah, I know this is not the best answer right now, but this is the largest question mark right now in the project. So on the one hand, the easier part of the answer is that we have, I think from the HLIG in Europe, we have a concrete set of guidelines where it is about ethical policies from IEEE, but these are very, let's say, formalized standards. The question is, how can we describe them in an operational manner in the DSL? But this, from my point of view, this is the easier part because there are existing standards and we need to find a transformation of that for a domain-specific language. What is more interesting is how can we somehow describe from an ethical perspective what discrimination is, that we also really, because there, as far as I understand, there's a lot of research already going out there, but I'm not that aware that we have, so let's say, concrete domain-specific languages criteria that allow us to describe what discrimination by algorithms would be. But this would be the prerequisite for our project that we can work on. Because right now it is very, very abstract what ethical policies would be. So this is a kind of ambition that we have, but currently we are looking for input for that question.
Yeah, that makes sense. Like there is two parts, right? How you transcribe your ethical standards into practice, and then maybe how you can verify it, right? So
Yeah, exactly. I think there are some kind of, let's say, if you take the skin color of a person, and this could be a criteria for discrimination. So this would be, let's say, kind of easier part if you determine that and make and look at that from an algorithmic perspective. But I do not think that this would be enough. I think that our research or ethical policies should go beyond that. But the question is, how, so to say, yeah? What are the criteria that would allow us to somehow evaluate whether discrimination is, whether the algorithm discriminates someone in a smart manufacturing context? So this is kind of complicated right now. And the easier part, as I said, is just to take the existing standards. Yeah, and I hope that we will contribute more than somehow finding a domain-specific language for explicating that, because I hope that we can contribute more to that. Yeah.
Yeah, thanks. That makes sense. Yeah.
Okay, thank you very much. So in an effort to combine speakers and answers, Carlos, you have a question for someone?
Yes, I do. Hi, Simon. So I noticed that you mentioned that you have found like some like tangled pipelines when you explore in the small domain. And I noticed that you have like a screenshot of a Jupyter notebook. And I have read like there's some backlash against like the popularity of Jupyter notebook among the data science community. And I wonder if you have some thoughts about like, are these tangled pipelines due to the Jupyter notebook? Can the tool play a role in these messy pipelines?
So I think both, like because of the Jupyter notebook and also because of the tasks they are performing. So in many cases, there are a lot of data exploration going on, like exploratory data analysis, which actually may not be the part of the final solution, but they actually try to come up with the solution with many data preprocessing tasks. And also we have seen like in the intermediate representation of the data needs to be analyzed, and you cannot like do everything beforehand and then do the modeling or training. So and as you said, like in Jupyter notebook, you can go back and forth, and the execution of cells are not that much organized. So we have seen both of these cases because of the inherent nature of the task, and also because of the this kind of IDs they are using. There are a lot of entanglement of stages in a certain stage of modeling. We have seen a lot of other stages like preprocessing or doing some visualization on the same stage. So yeah.
Oh, makes sense. Thank you.
Yep.
Thank you. Okay, and in order to, again, balance speakers, I'm going to jump in. I have a question for Zhengli. So your three principles are just enough, just in time, and just for me. Do you foresee that when it comes to reality, that there actually going to have to be trade-offs between those? And if so, how do you make decisions on what to optimize? Because they seem some of the characteristics that you had seem to be overlapping.
Yes, exactly. So it's really depends on the real situations. So I mean, I think could be different project by project. And for example, in our case, to improve the communication efficiency, sometimes we have to consider to weaken some features of some very sophisticated techniques, or we try to use even lower level, not that fancy techniques to in some relatively poor environment, so that we can balance the communication performance and also processing efficiency. So it's not just about the communication efficiency anymore, because we have to have the overall trade-off. So there's no single rule for that. So we have to discuss case by case, and there are always kind of trade-offs especially between the first two principles. For the third one, it's like we need, it depends on because it's a proposal at this current stage, or kind of the technical solution could be a semantic notification mechanism. So it'll depend on how fancy, okay, the semantic notification mechanism is. Okay, for the smart, but in the selfish guy, okay, if you want me to work for you, just speak my language, I don't have to understand yours. So it's like a single direction way to make the semantic notifications understandable between both.
I see.
Yeah.
Okay. Well, thank you very much. So there's a question from Gaston Marquez for Philip. I'm going to read it out. I would like to know if you have already had experience using Spring Eureka in your proposal. As you mentioned in your future work that you would use Spring Eureka, I am curious to know your experience using this technology.
Yeah, actually, when I wrote the paper, I did not have experience with Spring Eureka. So we began to use it. So it's currently in the proof of concept that we're working on. And yeah, I can frankly say that I made a lot of very positive experience with it. So I'm quite impressed, and I kind of begin together to become a fan of Spring Eureka, so to say. It's quite cool, yeah. That's just from a technical perspective, so it's not a research focus here.
Yeah. Okay.
Does this answer
Are there
the
any?
question?
Are there any specific, let's say, features like you're impressed by it? What are you impressed by?
Yeah, very frankly, it just works. So looking back on 15 years of software engineering practice, it's seldom the case that you just use a framework and it works out of the box without a lot of problems. So it really works reliably. And what I also like about it, that I can also give it to kind of say junior developers, and it just works and it's easy to explain. And yeah, this is the reason why I'm kind of impressed by it.
Yeah, it was funny. It just works. Oh, okay. I'm gonna go.
Sorry.
Yeah, I know it's fine. I'm gonna go back to Carlos. You said you had another question for Anas. Go ahead.
Yes, Anas. Like, I'm aware that there are some tools now for like traceability of requests in a microservice architecture. So I was checking some Amazon stuff, and you got really a lot of information. You can see how to request moves into every microservice, and you get a lot of logging. So I was wondering, with this like advanced tooling for traceability, there's still this gap that you have found between orchestration and choreography.
Mm-hmm. So all these tools, like, they do make the visualization for the developer easier, but I think the gap really is still the visualizability is kind of a bit hard when you, let's say, when you're talking about choreographed techniques, you cannot say or like be sure about where the request is going to be in, like, in a span of like let's say if the request is like going to be 10 seconds long, you cannot say where it's gonna be at in like 5 seconds, after 5 seconds, because you cannot like actually trace the request, or you can actually guarantee in 5 steps where the request is going to be or which microservice is going to be running. So in that end, we do believe there's a lot of work that needs to be done, but we can also say for sure that at least orchestrated techniques can make it easier to be sure of what step the request is going to be on, or enable practices such as static analysis and vice versa for that. But yeah, there is a gap, and that needs to be worked on.
Thanks.
Okay, and I believe there is another question for you, Anas, from Zheng Li. You wanted to ask him a follow-up question to your previous question.
Okay.
Yes. Actually, I have two questions, but I choose the easier ones first. The work you proposed is like a workflow engine, and at least according to my current understanding, I would like to call it as a controller. Okay, for now, let's agree with this. And there's a dilemma, I would say. For example, depending on the workflow you are going to handle, what if, for example, if there's a workflow that involves a lot of microservices, then your controller will become a new monolithic sport. And if you say, on the other hand, well, we can break the complicated workflow into sub-workflows, smaller granularity workflows, then there could be a possibility of the controller explosion. You will probably have to have multiple or probably even many controllers that to handle quite a few different sub workflows under the same much bigger workflow. So how do you deal with this dilemma?
Okay, so yes, we do use workflow engines, and we are strongly in favor of them. And another thing that these workflow engines, including Uber Cadence, Netflix Conductor, they offer the concept of a worker. So there is a separate process, or the server, that is basically handling the orchestration. It's basically, at the end of the day, registering events in like a hybrid choreograph technique, but it's generating events for that queue. And we have different controllers, as you said, but in the context of a workflow engine, they're termed workers. We have multiple workers that are actually hosting that process. So as soon as a request is generated in the queue of an orchestration engine, what it does, it distributes that process or that task in those workers, and these are the ones that actually host that process. So obviously, yes, you are correct on that end. You will need to have multiple workers, otherwise it's actually no distributed system.
Totally agree. May I follow up? It's closely related
Yes.
to my second question. So actually, I totally agree with this. I already have the answer to this question. The orchestration mechanism is unavoidable. That's why we have the quite a few microservice patterns, like a proxy pattern, integration pattern, and especially the API gateway pattern to address, to implement those type of, to at least handle multiple, loosely coupled microservices to work on the same workflow. And especially API gateway can do some, at least can address some issues proposed in your paper, like debugging, like security or performance monitoring. And even from the data consistencies perspective, because you used a ticket canceling example in your paper, right?
Yeah.
So that's a perfect example to demonstrate the distributed transaction. In the same transaction, we need to make sure the data to be consistent, at least eventually. And we already have mechanisms like a two-phase commit mechanism, or in the microservice community, a more advanced one is like the Saga mechanism to handle the data consistency for the distributed transaction. So we already have these type of so many different microservice patterns to deal with many issues you mentioned in your paper. So why do we need the workflow engine proposed by you? Or what makes your workflow engine unique rather than using the others? I assume your workflow engine cannot fulfill sort of one size fits all goal for all of this.
Okay, very good question. So the workflow engines that we explored, in addition to being orchestrated, they had other capabilities involved. They actually supported all these Saga principles and those gateway API that you mentioned. And there are like other multiple features that are actually implemented under the hood, and they really did come in handy. So the first of all was their nature, or their guarantees of being fault tolerant and fault resilient. So what they guarantee is, in case of a failure, or in case any of the steps in your process fails, it is automatically going to be recovered. Now, how do they do that? Is they have multiple retries options, and they do it automatically. It's done under the hood. You just implement tasks using their APIs, and in any case, in a case you feel that, okay, this task is going to be prone to failure, that's going to be implemented in a concept of temporal engine called activity. Now that activity is going to be repeated in case there's a failure in the request. And these workflow engines also make the guarantee that in case, okay, the failure has occurred, now what's the next step? Now the failure is going to stay, the process is going to stay in its queue or in its state with everything preserved. And as soon as, the changes or the fixes have been made, it automatically resumes. So these are some guarantees which are actually going to be really helpful for the community, and that is why we make claims such as when we say that, okay, these could be the next SQL for workflow engines or microservices. So there are other guarantees that are basically involved, which are actually highlighted in the paper itself as well. So thank you for the question, though.
Oh, thank you. Thanks.
No, thank you. Thank you all. So in an effort to give you a little bit of time to go to your next session, they're really good ones at noon. Thank you again to all. Thank you to Henry Tang, our student volunteer, who was really good at helping me keep track of which questions have been answered. So I appreciate that. So thank you all. I hope that you all keep in touch, given that you're working in the same area. It was very sad for me to hear from the opening presentation. I don't know if you all felt the same sadness that when Andrea Zeller said that software architecture was one of like the smallest topics and one of the most, I think he used the word most rejected, meaning that where most papers were rejected. And that's a shame because obviously this is an area that is close to my heart. So keep doing good work and hope to see a lot more presentations and papers in this area next year. Take care. Have a great rest of your day.
Thank you very much.
Bye-bye.
Thank you. Bye.
Thank you.